Hello, you internet folks. This is Bamboozling Bit with another video that will wrinkle your brain. Or it may not. Maybe you already know this. Who knows? So, today we're going over a definition of divisibility, okay? Okay, so we're going to have a recap of what number theory is, because perhaps this is new to you. So, you have to know that number theory is concerned with integers, okay? Integers are numbers without a decimal portion, okay? So, for instance, the number pi is not an integer. Why? Because it has a portion of decimals. 1, 4, 1, 5, etc. Okay? So essentially what you're going to have, like, for instance, the square root of 2 is not a integer, but negative 1, 0, 1, those are integers. Okay? So you can go from negative infinity up to positive infinity with these integers. Okay? So now, traditionally, number theory is a branch of pure mathematics, but just know that it can be used for discrete math, particularly encryption algorithms, but we won't delve into anything that is like RSA or SHA-256, okay? However, what we have to know is that we're going to use it for divisibility theorems, okay? Okay, so let n and d be two integers where d is not equal to 0. We say that d divides n if there exists an integer q such that n is equal to d times q. Just know that q is the quotient and d is a divisor or a factor of n. You see how there is no remainder, right? And this can be basically shown through symbols, okay? So we put the d before the large stick, and then we put the n, okay? Now, one implication that we have in here is that n can even be 0, right? And if n is 0, any integer but 0 can divide it, okay? So d could be any number but 0, okay? Now, if n is equal to 0, guess what is the value of q, okay? 0. So, what we're following right now is this proof of this statement, okay? In reality, just to keep more formality in this statement, the n plus m should be used by commutativity of addition. We don't care, right? Besides, addition is a binary operation that is closed under the integer set. Why? Because the sum of two integers will always result in another integer, in case you didn't know. So now, what is going to follow is the proof of this statement. So if d divides n, there exists an integer q1, okay? And this said is the integer set such that n is equal to d q1, right? Now, if d divides m, then there exists an integer q2 in said such that m is equal to d q2, right? That is the case that we're going to have, okay? Thus, it is the case that n plus m equal to m plus n is going to be equal to d q1 plus d q2 just equal to d q2 plus d q1, okay? And this, if you can see that we can factor out the d. So you can see how the proof goes. By no means is this the quickest way to do it, but is the most comprehensive one, in case you want to understand it at a more granular level, right? That's what I'm seeking, okay? So you have here that you have d times q1 plus d plus q2. all within a parenthesis. And by commutativity, okay, it's going to be D times Q2 plus Q1, right? And we can add meaning N plus M divided by D is equal to M plus N divided by D, right? Which is equal to dq1 plus q2 divided by d, which is equal to dq2 plus q1 d times q2 plus q1 divided by d, okay? Which is going to be equal to q1 plus q2, which is equal to q2 plus q1. Why? Because we can cancel out the d's, okay? Hence, if d divides n, and this is a logical and, d divides m, we can say therefore, we can say thus, can be interchangeable. You can use the arrow, you can say, then d divides n plus m, okay? And that's the end of the proof. You can see that just with that, you can prove the first part of the theorem, okay? Which comes in 3 parts. We're gonna go with the second one, okay? We're gonna go with the proof of the following statement. By the way, there's not two Carlos Lopez. I mean, this one has Alberto. It's not a different person, it's just my iPad, okay? So now we're gonna go with the proof of the second statement, okay? So if d divides n, remember, there exists integer q1 in the an integer q1, okay? Such that n is equal to d times q1, and if d divides m, there exists an integer q1 in said such that, I mean q2, it would be an integer q2 such that m is equal to d times q2, okay? Thus, m minus n. So we're gonna have to have 2 cases here, right? We're gonna go with the first the proof that d divides m minus n and the d divides n minus m, okay? Because there is no commutativity in subtraction, or does matter in subtractions of integers. Just know that subtraction is it's an operation that is closed under the integer set, meaning that if we subtract one integer from another integer, it will result in another integer, okay? It's going to be equal to d. But actually, let's go with a more ordered version, okay? So we're going to have that n minus m. It's going to be equal to d q1 or d times q1, okay? D times q1 minus d times q2, which is equal to d q1 minus q2, okay? So you have to know that one. D times q1 minus q2. Meaning that n minus m divided by d is going to be equal to d q1 minus d q2 divided by d, which is equal to d q1 minus q2 divided by d, which is equal to q1 minus q2. Hence, d divides n minus m, okay? Now, m minus n is going to be equal to dq2 minus dq1, right? Is equal to dq2 minus q1, okay? Meaning that dq2 minus q1 divided by d, but actually there's a step missing in there. Wait, I skipped some steps. So you're gonna go with m minus n divided by d. It's gonna be equal to dq2 minus d times q1, okay? Divided by d, which is equal to q2 minus q1, okay? But I skipped some steps. Forget. It's equal to dq2 minus q1 on the parenthesis, which is equal to q2 minus q1, okay? So you can see that these cancel out and you end up with q2 minus q1, right? So you can go with that one. Hence, d divides m minus n. In conclusion, if d divides n and d divides m, then d divides n minus m and d divides m minus n, okay? And that'll be the end of the proof. For this case, this one is more extensive, but it is pretty thorough. Obviously, there's more efficient ways to write this, but I suggest that if you want to comprehend it more completely, you do it like this. You read it more carefully, and you'll see that you'll just need to follow some steps. For instance, just factoring out the d is more than enough to show it, okay? I can go over it perhaps in another video, a more efficient way to prove this, but just know that this is the more extensive and thorough way to prove this second part of the theorem, okay? The last part of the theorem, okay? Which is that if d divides m, then d divides m and n, regardless of whether d can divide n or not, okay? So we're going to use a proof by case, okay? So we're going to see in the first part that if n can be divided by if n can be divided by d, we can still divide the multiplication of m and n. And in the second part, we're going to see that if d cannot divide n, meaning there's a remainder, it can still divide the product of m and n, okay? So if d divides m, come on, then there exists an integer q1 in the integer set, okay? such that d is equal to m is equal to d times q1, okay? That is a case. So you can go with case 1, okay? Case 1, d divides n, okay? Here we have that if d divides n, then there exists an integer q2, okay? Such that n is equal to d times q2, right? So that is the case, okay? So in that case, we're going to use that one. And following on, we're going to see that m times n is going to be equal to d squared q1 q2, okay? And you can see that it is d squared because we have dq1 times q2. And in case you didn't understand that portion, we can say that this is dq1 times dq2, which is equal to d squared q1 q2, okay? Meaning m over n divided by d is going to be equal to d squared q1 q2 divided by d, which is going to be equal to d times q1 times q2. Hence, d divides m and n, if d divides m and d divides n, okay? Now we're going to go with case 2. D cannot divide n, okay? D divides n. If d cannot divide n, then, okay, d cannot divide n, then there exists integers q2 and r in the integer set, okay? Remember, they exist such that n is equal to d times q2 plus r, okay? And this is a very extensive case. Like, obviously, there's more simple ways to prove it. I'm going to go over the most efficient way, but I want you to understand that this is a more extensive proof of it to get into more efficient mathematical proofs, okay? At least for discrete math, okay? So now we're going to have this, okay? You can say that thus m times n is going to be equal to d q1 times dq2 plus r, okay? Just equal to d squared q1 q2 plus d times r, right? Which is equal to d times d q1 q2 plus r, okay? And that'll be it, okay? For at least the initial part, okay? So, meaning m times n divided by d is going to be equal to d squared q1 q2 This is dr divided by d, which is going to be equal to d q1, q2, this r. So you remember it's d multiplying this portion that is within the parenthesis, as you can see. We have a d in here, and this is going to be equal to d times q1 times q2 plus r, okay? Hence, if d divides m and d cannot divide n, then d divides m times n, okay? So we conclude, so in conclusion, we can say that if d divides m, then d divides m times n, regardless of whether d divides n or d does not divide n, okay? That is the end of the proof. This is a more extensive version. I just want you to see that there is a lot of logic in it, but it is not the most efficient way to prove it, okay? As shown, the theorem below is true. Let m, n, and d be integers. So if d divides n and d divides m, then d divides m plus n, okay? If d divides n and d divides m, then d divides m minus n and d divides n minus m, okay? So if d divides m, then d divides m times n, regardless of whether d divides n or not, okay? Now, remember when I told you that I was going to show you the most, like one of the most efficient ways to solve the proof of the divisibility properties theorem? Well, here it is. You start with a proof of A, a proof of B, proof of C, and then you use those three proofs as corollaries and thereby establish a formal proof for the divisibility properties theorem. You can see that it is more concise than the other one, and it is quite clear, okay? That'll be it. Okay, thank you for watching this video, folks. Just trying to proliferate some computer science knowledge, and you can subscribe to my channel or profile, and I would love that.